Okay, and now I'm going to start to record. Okay, so good afternoon, everyone. It's a pleasure to have you all here for this afternoon section. And now I will pass my word to Professor Carlos Bessa, who is going to introduce our next invited speaker. So, Carlos.
Okay, John, thanks a lot. Thanks, Professor Larry Ford. I'm very glad to have you here with us. And Professor Ford is a professor from Tufts University in the USA, and he got his PhD at Princeton University in the USA. And then he made like a couple of postdocs, one on the Wisconsin, University of Wisconsin, the USA, and the other in the King's College London, the UK. Okay, Professor Ford, have a nice talk. Thank you very much.
Okay, well, thank you for the introduction, and thank you for the invitation to speak to this meeting. So, as you can see from my title, I'm going to be talking about quantum stress tensor fluctuations. Let me tell you a little bit about what those are. So, first, let's talk about the stress tensor in both classical and quantum physics. So, of course, as you know, the stress tensor actually has various roles. It was originally introduced, I think, in the 19th century as a way of describing things like energy densities, fluxes, and especially forces on material objects, that is the Maxwell stress tensor, for example. So the different components, so of course, this is represented as a 4x4 matrix. The different components include things like energy density, energy flux, but also pressure and stress components. And this is going to come back a little later in the talk when I talk about fluctuations, because that means there'll be fluctuating forces. But in gravity, we're especially interested in this because the stress tensor T mu nu sits on the right-hand side of Einstein's field equations, and it acts as the source of gravity. So it is the analog of the current density in electromagnetism, the source for the, just as the current density is the source for the electromagnetic field, the stress tensor is the source for the gravitational field. But here, today I'm going to be talking about situations where the matter is quantum. Gravity itself may not be quantized, but the matter is going to be quantum mechanical. So if we're going to need, for example, like a quantized electromagnetic field, this becomes a quantum operator. And in general, the quantum states that we're interested in, so for example, on a flat background, the vacuum state, for example, is not an eigenstate of this operator, which means there are necessarily fluctuations. If you made measurements of the energy density, you would get varying values. And that's what we want to understand a little bit more clearly in this talk. So first of all, there are going to be effects of these fluctuations that lead to force fluctuations on material objects, but also it will lead to fluctuations of the gravitational field, which I call passive fluctuations because they're basically driven by the quantum matter fluctuations. So if you have a large fluctuation of the energy density or of the components of the stress tensor, that will drive a fluctuation of the space-time geometry. Now, this is different from the effects of quantizing gravity itself, which you might call active fluctuations, when the dynamical degrees of freedom of gravity fluctuate. But nonetheless, passive fluctuations are still an interesting quantum gravity effect. And something that are useful to understand is on the way of understanding quantum gravity in a more complete way, because they have to be part of any complete quantum description involving both matter and gravity. Okay, so let's first back off for a moment and talk about fluctuations of linear operators, like the electric field operator, for example. So first of all, before we can discuss fluctuations of a local operator, we have to average it in either space or time. Because in fact, as we'll come back to, if you look at the operator at one space-time point, its fluctuations are not well defined. They're basically singular. This of course is tied up with the uncertainty principle. Just as you can't localize a quantum particle precisely in space without having infinite energy, you can't talk about the quantum fields in too small of a space-time region without dealing with states with arbitrarily large energy. So we imagine we take an average, and this, of course, is what a measurement does anyway. Any true measurement is going to involve an average over a space or a time region. So let's imagine that we have some sampling time, which describes our measuring apparatus, and suppose it has a characteristic width tau. So we average the electric field operator over this. In this case, I'm doing just averaging in time. So I just pick a point in space and average in time. So when we do that, we find that in the vacuum state, the mean value of the averaged electric field is 0. But that's because it's equally likely to be positive or negative, fluctuate equally around positive and negative values. If you look at the variance, that is the expectation value of the squared average field, that typically is proportional to the inverse fourth power of the averaging time. And this is where you see the confirmation of the statement that the local operator doesn't have meaningful fluctuations. As you let tau go to 0, of course, this variance goes to infinity. And for the most part in this talk, I'll be dealing with units where h bar and c are set equal to 1. So that means that energy densities or squared electric fields have dimensions of length or time to the -4 here. And that means also that e squared times tau the fourth is a dimensionless quantity. Now, the electric field satisfies a Gaussian probability distribution, as is well known. So the probability of finding a given value, suppose we do a measurement that measures the average electric field, with, for example, some test charges. And we do repeated measurements and we plot the outcomes of those measurements on a histogram, we'll get the usual normal distribution, Gaussian distribution associated with a random process. That is, the probability of finding a large value of E bar will scale down as the exponential of E bar squared. Now, the quantity in here is this dimensionless measure times a constant, typically of order 1, but the numerical value of that constant depends upon your choice of the sampling function. Use different functions, you'll get slightly different values for this constant. And you get similar results if you do space averaging. You could average in either time or space or both, and they'll all give you something of this form, but with a slightly different constant. If you average just in space, then you replace tau by the sampling time by a sampling length, but everything is the same. And of course, this Gaussian result is tied in with the well-known fact in quantum mechanics that the ground state of the harmonic oscillator in the Schrödinger, the representation is a Gaussian function. If you have a harmonic oscillator, the probability distribution of finding different values of the displacement or the momentum of the operator fall off as a Gaussian of those variables. But we'll see in a moment that when we go from linear fields to quadratic fields, things change dramatically. So let's look now at quadratic operators, such as the squared electric field or the energy density, which is quadratic in the electric field squared and the magnetic field squared. Now, I'll quote some results. I won't have time to go through, and we'll talk about some of them a little bit more in this talk, but I won't have time to explain all of them today. But one result is that time averaging is essential. You can and often do want to average in space as well, because the space-time measurement often does involve averaging over space. But if you just took the squared electric field and averaged it just in space, it would not produce finite fluctuations. And I'll say in words the reason for this, and that is that if we went back to the electric field itself, of course, as you perhaps know from quantum field theory, this can be expanded in a series of normal modes, often plane wave modes, with creation and annihilation operators as coefficients. And each of those would be multiplied by a plane wave, which is an exponential in x and an exponential in t. So if you average in time, you would effectively be taking the Fourier transform of the time averaging function, which will tend to fall off for large values of its argument. If you averaged in space, you would be taking a spatial spatial average of the averaging function, which also will decay for large values of the argument. But now when we go to the case of quadratic operators, you're averaging something a little more complicated. You're averaging a double sum involving products of plane wave modes. And the crucial terms will involve things that involve like e to the exponentials in time, e to the minus I omega plus omega prime times t, where omega and omega prime are the frequencies of the modes. If you average that, that's still in time, that still gives you a Fourier transform that falls off. But the spatial part involves a sum, something like e to the I k, vector k plus vector k prime dotted into x. If you average that in space, that doesn't fall off in the for the modes where the cases of the pairs of modes where they're in opposite directions. You don't get suppression. So that's why, that's kind of in brief why spatial averaging alone is not enough. And we'll see a physical effect of that later in this talk. Okay, number two, this is a highly non-Gaussian distribution. For example, the odd moments are typically non-zero, unlike with the linear field. So it's also a skewed distribution. But even more than that, if you're dealing with a quantity like squared electric field or energy density, which is classically positive, then the probability distribution, then there's a lower bound on the expectation values of the quantum operator, which is called a quantum inequality. Now, you might be a little bit surprised that energy density can be negative in quantum field theory. That's actually the subject of a completely different talk. But in fact, you can create states in quantum field theory where the local expectation value of the energy density is negative, but it just can't be too negative. Or if it's negative, it can only be negative over a very small interval of time, not over a very long interval of time. And there are what are called quantum inequality bounds that limit that. So that means that the probability distribution actually has a lower bound on it. That is, the tail of the probability distribution, this is basically a lower bound on the probability distribution at some finite negative value. It actually cuts off. But there's no upper bound, that you can have arbitrarily large positive fluctuations. And another interesting feature that we'll discuss in a moment is that the tail can actually fall very slowly, that you can find unexpectedly large positive fluctuations. Okay, so let's now imagine that we take some local quadratic operator, such as the energy density or squared electric field operator. I'll write down, and we imagine we're in a vacuum-like state. Right now, I'll talk in flat space-time, but everything I'm saying can be generalized fairly easily to curved space-time. But let's imagine explicitly in flat space-time. Let's average this both in time and in space. Although we could always get rid of the spatial averaging if we wanted to. So there's a function in time with some characteristic time width and some function in space with also a characteristic spatial width. And we'll define a dimensionless quantity, which we might take to be the sampling time scale to the fourth power times the averaged operator. So this is a dimensionless variable. And we're going to look for a probability distribution. What is the probability of finding a given value of this variable in a given measurement, which is equivalent to finding a given value of the averaged operator? Now, briefly sketch two ways to approach this, which can be used. One is the computation of the moments of the distribution, and the other is what's called a numerical diagonalization procedure. So let's first talk about moments. Well, first, so let's go back for a moment. So when we do this averaging, in effect, we're damping out the high frequency modes in either especially with the time averaging, as we saw, as I explained to you briefly, the spatial averaging isn't quite adequate to completely damp out all the ultraviolet divergences, which is why you need time averaging. But the effect of the averaging is that it is going to suppress the high frequency modes and give you finite fluctuations. But these functions f and g should have a physical meaning. They should actually describe the outcome of a measurement process. And I'll give some examples of that later in this talk. But more than that, the functions f and g should describe a measurement that occurs in a finite space-time region. And that means they're going to be described by functions that are strictly zero outside of a finite interval, which mathematicians call these functions of compact support. That just means the compact support just means for a function just means the region in which the function is non-zero is a compact set. So the reason we want those in physics is we want the measurements to begin at a finite time in the past and end at a finite time in the future. So the sampling function in time should be strictly zero outside of those times, which means that it cannot be an analytic function. But this would be a better, more physical choice. If you have something with a switch where you turn on and turn off at a certain time, then that switch is not described by an analytic function like a Lorentzian or Gaussian, which infinite tails extending into the past and the future. And these, although these are useful models, Lorentzian and Gaussians are useful models for many purposes. They're unrealistic in this sense. And of course, our spatial region should also be finite, have compact support as well. Okay, so let's now look a little bit more at functions. So imagine that f is a compactly supported function of time and g a function of space, which means zero outside of a finite interval. Let's look at the Fourier transform, the temporal Fourier transform of f of t and the spatial Fourier transform of g of x. Because these are compactly supported functions, you can show that these, but we also want them to be infinitely differentiable, C infinity functions. They need to decay faster than any power of their argument, the magnitude of their argument. But most importantly, they need to decay more slowly than an exponential. So for example, one possibility, which is a wide class of these functions, is that f hat as a function of omega might decay as an exponential of a fractional power, omega to the alpha, where alpha is less than 1. And in fact, one can construct explicit functions that fall into this category for different values of alpha. And in fact, it's possible to construct a simple electrical circuit which corresponds to the alpha equals 1/2. Namely, its Fourier transform falls off as the exponential of the square root of the frequency. And its switch on in time basically looks something like this. So this switch so if you look at the function e to the minus 1/t, where right now t is a dimensionless time, as t goes to 0 from above, this function goes to 0 faster than any power. So it's strictly 0 at t equals 0 or before t equals 0. So this is an example of a function that switches on at time t equals 0. So if you plotted this function as 0 at t equals 0, and then it rises up to a maximum and then falls off again. And the fact that you have these relatively high frequency Fourier components in the spectrum of this function comes from the fact that it was switched at a finite time. In other words, anytime you flip a light switch, you have some probability of getting relatively high frequency photons that come from this switching process that are somewhat higher in frequency than the mean photon in the light. And that's just a matter of simple Fourier analysis. So measurements in finite intervals then may lead to significant contributions from the high frequency modes. And that's going to play an important role in what I'm going to talk about next. So if we now go to the moments approach for discussing the probability distribution, which is discussed. So this was developed in a couple of papers with Chris Fuster. So the moment is defined as the expectation value, let's say in the vacuum state, was our chosen state, of the nth power of this averaged operator. And in general, the moments tell you something about the probability distribution. Under certain conditions, the moments uniquely define the distribution. But even if they don't, they tell you something about how fast the distribution falls off. So in particular, for time averaging alone, you find that the moments grow relatively rapidly. They grow as 3n over alpha factorial for large n, which is very high growth, rate of growth. The Gaussian distribution, the moments grow only as n factorial. And the asymptotic form of the distribution that has this rate of growth is basically an exponential of minus x to the c, where c is alpha over 3. So if you think about this, so if we take alpha equals 1/2, which is a physical choice, we can construct an apparatus that switches on with that. That means the exponent here is x to the 1/6 power. Now, if you compare how slowly x to the 1/6, e to the minus x to the 1/6 falls off compared to e to the minus x squared, is an enormous difference. That is, if you took x to be a million, 10 to the 6, you still get, if a is of order 1, you still get a non-trivial probability of finding that. Whereas, of course, for a Gaussian distribution, that would e to the minus 10 to the 12 is a ridiculously tiny number. So the form of the switching function is very important, because this parameter alpha, coming from the nature of the switching, ends up inside this exponential. And if switching in finite time, namely the fact that you have to have alpha less than 1, can produce very large stress tensor fluctuations. So in particular, if you average on however, if we average on a if we average in space as well as in time, you get somewhat more complicated behavior. Typically, what happens is that if the spatial scale is small compared to the time scale, then you get this world line behavior for a while, e to the minus x to the 1/6, for example. But then after a while, that transitions into a different behavior, x to the alpha. Remember, you had to have time averaging. But if you also have averaging in space as well as in time, then it suppresses the probability of large fluctuations. This exponent goes from alpha over 3 to alpha. But that still is if alpha is 1/2, that means the probability distribution is growing like an exponential of a square root minus a square root, which is still very small growth, growing slow, falling very slowly compared to a Gaussian. And you still have fairly large probability of large fluctuations, which could have some dramatic physical effects. Okay, so let's talk about the other approach briefly, which is numerical diagonalization. So that was developed in some other papers with Chris Fuster and Enrico Schiapacassi, and some work that's being done now and is about to appear with Peter Wu. But the idea is that the average stress energy tensor operator, as I implied, if you write it out in terms of, we assume it's normal ordered in the vacuum state, you write it out in terms of creation and annihilation operators, it has this quadratic form. And these off-diagonal terms are very important, but it can be diagonalized by what's called a Boglib transformation, a change of basis, where you transform the annihilation operators from one set to a new set involving the B's. And you find a set that basically kills off the off-diagonal terms and also the I not equal to j terms and renders the operator in this form. And this form is diagonal. The eigenstates here are just number eigenstates in the new basis. So we know what the eigenstates are, and we can find the probability of a given eigenvalue is just the squared overlap of this state with the vacuum. The physical state is the vacuum. So if you make a measurement, and you look for what is the probability if you're in the vacuum state to find a particular eigenstate of this operator, well, it's just the absolute square of the overlap between that operator and the vacuum state, which can be calculated. Now, this has to be done numerically. It's too difficult to do this analytically. But in fact, in numerical diagonalization, you actually can plot a distribution, and it basically agrees remarkably well with the moments approach and its qualitative behavior. So that provides support that this approach is on the right track. Okay, so let me go through a little bit about some of the possible physical effects of these fluctuations. So remember so first let's talk about effects in gravity. Because if you have a large stress tensor fluctuation, it means a large gravitational field fluctuation. And you might, for example, imagine that these effects might occur in the early universe. So now, of course, in order to understand them, you have to ask a little bit about what causes the switching. What is it that's doing the averaging? So it could be different things. It could be, for example, phase transitions in the early universe, the end of inflation, for example, the transition from an inflationary expansion to a radiation-dominated universe might do a time averaging of a quantum stress tensor. But in all cases, you'll create some fluctuations. And those fluctuations will basically give non-Gaussian perturbations, basically gravitational perturbations. So for example, in cosmology, we're often very interested in the primordial spectrum of what are called both scalar and tensor perturbations. The scalar perturbations are the density perturbations that later grow to become galaxies. And the conventional picture in inflation is that this primordial spectrum is approximately Gaussian, And it comes from the free field fluctuations of an inflaton field, which is believed to drive inflation during the inflationary period, hence giving the Gaussian spectrum. But there could be non-Gaussian components superimposed on that, and stress tensor fluctuations could be one of those. Now, so far, we haven't seen any evidence of non-Gaussianity in things like the cosmic microwave background radiation. But there's still a chance of possibly seeing that. And of course, that could come from either interactions of fields, or it could also come from large stress tensor fluctuations. So that's an area of interest to try to understand these. And they could also contribute to what are called tensor perturbations or gravity wave perturbations, which have not yet been detected, but are also predicted by inflation. They would show up as things called B modes in the microwave background radiation. They also haven't been detected, but they could also be sourced by large stress tensor fluctuations, as well as by the free graviton field in de Sitter space. So both of those are possible effects that could potentially be detected, especially in the microwave background radiation. Another effect is that if you had a very large stress tensor fluctuation, large energy density, you could possibly create a primordial black hole. If you imagine an energy density fluctuation that was large enough so that you push a little bit of matter within its own event horizon, it basically will collapse to become a black hole, and then either be stable or evaporate by Hawking radiation. And of course, there's been quite a bit of interest in primordial black holes, which could come from many different sources. But anytime you have a non-Gaussian component, and especially a large non-Gaussian component, it has the potential to create primordial black holes. So this is also an area of interest, which is being researched. And the stress tensor fluctuations, this is another place where you might look for the effect of stress tensor fluctuation in either primordial black holes. In the case of stress tensor fluctuations, they're probably less likely to create very massive black holes, like the things that have been seen in LIGO, than to create very small black holes that might have Hawking evaporated. But they would still leave an imprint, because if you created small primordial black holes in the early universe, but they persisted for a while before they evaporated, they'll change the thermal history of the universe. And there's a lot of study being done on that, which how these might change. They might be indirectly detectable through their effect on the microwave background radiation or primordial baryogenesis or other effects, or nucleosynthesis that should have occurred in the early universe. Now, I'll talk here briefly about a couple of other effects that can come from the large stress tensor or quadratic operator fluctuations. One which was discussed in a paper a few years ago with Haiyun Huang is on barrier penetration by quantum particles. Because as you know, if you have a quantum particle, charged particle, in quantum mechanics, we can calculate its rate to go through a quantum barrier through quantum mechanics, such as using the WKB approximation. And that's usually exponentially suppressed. If the particle has an energy well below the barrier, its tunneling rate is exponentially small. But there's a small chance that you might get a large radiation pressure fluctuation, because radiation pressure is essentially a component of the stress tensor. That is, it's well known, for example, that if you shine light on a charged particle, it exerts a force on a radiation pressure force, and that at the classical level. But there will be quantum vacuum fluctuations of that radiation pressure force. And if those fluctuations are large enough, and they satisfy a probability distribution that falls off more slowly than exponentially, it could give a contribution that is actually larger in certain regimes than the result that you get from from the WKB approximation, say, in quantum mechanics. So under very special circumstances, it might dominate barrier penetration. Now, you won't see it in most of the barrier penetration experiments that are usually routinely done in the lab, because those are relatively low energies. And you find that the radiation pressure contribution is exceedingly tiny. So it's not going to upset squid devices or any other things that have been well studied. But it might show up in nuclear physics. One mystery in nuclear physics is that experimental nuclear physicists found some years ago when they created heavy ion accelerators. Heavy ions means nuclei of elements like oxygen and nitrogen. And then they accelerated those and hit very large nuclei with them to cause the nuclei to fuse. The fusion rates were dramatically larger than were predicted by the as you expect by naive models of barrier penetration, because there's normally a very large Coulomb barrier that has to be overcome, and the nuclei were getting through that Coulomb barrier for reasons that are still not well understood. Now, there are conventional nuclear physics explanations that have to do with the deformation of the nucleus and other effects. But in this paper, we also pointed out that radiation pressure fluctuations could be large enough to explain this anomalous effect. So it's not yet known, but there's a faint chance then that this effect has already been observed, but we don't. More work will be needed to confirm that that's really the correct explanation. There's an analogous effect that we pointed out in a recent paper earlier this year of what's called false vacuum decay, which was studied by Coleman in the 1970s by what's called bubble nucleation, which again is a tunneling process analogous to the tunneling of a quantum particle. And it's usually described by an instanton approximation, which is very much like the WKB quantum approximation in quantum mechanics. However, large quadratic operator fluctuations can actually also enhance the rates of that, as we showed in this paper, and possibly increase the rate of decay of the false vacuum under certain conditions. So again, this is a somewhat controversial, but it's a possible effect. But the last part of this talk, I want to talk about an analog model where you're dealing not with gravity, but some other quadratic operator that models an effect like that in gravity. In particular, I'm going to talk about quantum density fluctuations in a fluid. So for example, if you imagine a fluid and you quantize the vibrations, these are essentially the phonon modes of the fluid, there will be quantum fluctuations of the density of the fluid, as is well known. And it's been shown in the past that those fluctuations are described by an operator, the density operator. But unfortunately, the word density operator in statistical physics means something completely different. This is really a quantum operator that describes the actual mass density of a fluid. And it takes the following form. It's proportional to the square root of the mean mass density of the fluid divided by the square of the mean square speed of sound in the fluid times the time derivative of an operator which formally looks just like a massless scalar field in relativistic quantum field theory, except that you replace the speed of light by the speed of sound in the mode functions. But it looks very much like phi dot. So of course the fluctuations of this operator will be Gaussian fluctuations because they're the fluctuations of a linear operator. But we're going to be also in a moment be interested in the fluctuations of the squared density, which will involve fluctuations of a squared operator, which will have, again, the non-Gaussian fluctuations. But first, let's talk a little bit more about the linear fluctuations of the fluid. those will lead to light scattering, as I discussed in a paper some years ago with Nami Spider, where we showed that the cross section for scattering of light off of a fluid can be written in this form. Is basically proportional to the scattering volume, the index of refraction of the fluid at the wavelengths you're dealing with to the fourth power, divided by the speed of sound, the mass density, and the fifth power of the mean wavelength of the fluid. And as we argued in this paper 10 years ago, this does seem like it's potentially observable, but it has, so far, no one has managed to observe it yet. But it's still possible that these fluctuations could be observed. But today I want to tell you about another effect, which is the fluctuations of the squared density, which are the result of averaging over finite space and time region by finite size photon wave packets, which is some work in a recently published paper with Peter Wu that just came out a couple of months ago. So the idea is we're going to use a wave packet, which is described by compactly supported functions of both space and time, to average the squared density operator and look at the effects of that. So now we're averaging the square of a quadratic quantum operator. And because the speed of the packet is much larger than the speed of sound, the effective averaging time is going to be very, very short. I'll show that on a space-time diagram in a moment. So it's going to lead to large density, square density fluctuations, because it's like averaging a relativistic field over a space-like interval. And we can understand that a little better on this what you might call a sound cone diagram. So this is position and speed of sound times time. So of course, this is like an ordinary light cone, except for sound waves. So this dashed line is what you may call the sound cone. It's the path of a phonon in this, or a sound wave in this fluid. The light ray comes in and travels much orders of magnitude faster than the speed of sound. So it's traveling at almost infinite velocity compared to the speed. The speed of sound, of light in a liquid, is typically 5 orders of magnitude larger than the speed of sound. So this is almost a level thing. So the light path goes through here on a very small time scale in this diagram. So tau is the time required for the light pulse to go by a certain point. L is the length in space of the pulse seen by an observer at a given time. So this dark red square could represent the light pulse at a given moment in time. So let's imagine now that it scatters off of a given region of size L, and we're going to catch the scattered photons that come from a given measurement, as shown here. The pulse is going this way, we're going to catch some scattered light. Now, because we're looking at a measurement over a finite region, we're going to look to the square density fluctuations are going to lead to large variations in the number of scattered photons. So they can go up or down by a large amount. So remember, this is the mean number that came from that formula for the total cross section that I showed you a moment ago. We're now going to, as a result of fluctuations in the squared density, we're going to get a variation in the number of scattered photons. This is going to be the quantum effect due to the finite averaging. This is essentially the same thing as what went into the cross section. This is the number of photons in the wave packet. So this is how many you typically expect to see scattered in a given measurement. So So what we're interested in is the ratio of this variation in the number in a measurement to how many you would have expected just from linear fluctuations of the field. So here I'm just going to quote some brief results here. We chose liquid helium-3 just because it's you want to do this at low temperatures, and and you want something that's not a superfluid. Helium-4 becomes a superfluid at too high of a temperature, whereas helium-3 becomes a superfluid only at very, very low temperatures. So imagine you had a wave packet whose length in space is about 400 micrometers. This is the index of refraction of liquid helium-3. This is the speed of sound of liquid helium-3. And we'll just take a mean wavelength in our wave packet of about a micron. So it's small compared to the size of the wave packet, but it's not too short. So what you see here is that we predict that this typical variation due to the wave packet is maybe about 12% of what you have had anyway. So that's a large enough fraction. If you send a sequence of wave packets through with these parameters, we're predicting that if you average overall wave packets, you'll get this average value NS, but in any one measurement, you'll typically see values maybe 12% above or below that value, which is potentially large enough to be observable. Now, of course, you want to compare this with a couple of other effects. One are statistical fluctuations. Just due to the fact that NS is a finite number, there will be statistical fluctuations. But that you can, if you make NS large enough, you can suppress those. So if you want to compare the delta NS, the fact that we're looking at, as compared with statistical fluctuations with the same choice of parameters, what you need to do is to make sure that the energy of the wave packet is large enough so that the mean number of photons is large enough. So about a microjoule at this wavelength is enough. If you use a microjoule, then in fact, the effect we're looking at is an order of magnitude larger than the statistical fluctuations, so you can tell them apart. You also want to make sure that it's different from the thermal fluctuations just due to finite temperature. But that's okay. If you go down to temperatures below about 1/10 of a Kelvin, then in fact the thermal effect will also be suppressed. So potentially you could observe this. So I think I'm about out of time, so let me quickly summarize what I've told you here. So basically, most physical states are not eigenstates of the energy density or other operators. They're quantum fluctuations. They can lead to fluctuating forces or passive fluctuations of the gravitational field. They require fluctuations to be averaged in time at least. And this averaging represents the measurement process, which occurs in a finite region. And this means we need non-analytic functions whose Fourier transforms decay relatively slowly. And that means then that you get a non-Gaussian probability distribution that falls more slowly than exponentially, an enhanced probability of large fluctuations, which can lead to various effects that I've discussed, enhanced effects of quantum tunneling, false vacuum decay, and non-Gaussian density and tensor perturbations in cosmology, perhaps primordial black holes. But especially in what I've just told you about, possibly large density fluctuations in a fluid that could be enhanced, possibly might be observable in an experiment where you do scattering of pulsed light, an experiment which, according to the estimates that I gave you, looks like it might be a feasible experiment. So I'm hoping to encourage some experimentalists to consider actually doing this experiment, because there's clearly it's much easier to see density fluctuations in a fluid than it is to see quantum fluctuations of the gravitational field. But they would also tell us something deep about this. So I think on that note, I should stop and leave some time for questions.
Okay. Okay, let's see if anyone has some questions. You can write here in this Q&A section. So far, we have no questions. Let's see in the chat. Ok, I'll say the same thing in Portuguese now, because some people... Se alguém quiser fazer perguntas, pode escrever aqui nessa seção Q e A. Pode ser em português, eu traduzo.
Carlos.
Yeah.
We have a participant here who raised his hand.
Oh, okay, I'm not seeing this. I'm not seeing raising hand.
Joaquim Rodrigues. Okay. I'm going to allow you to talk if you want to talk something, Joaquim. Pode falar, Joaquim, se você quiser fazer uma pergunta ou falar algum comentário.
Tá de boa aqui, beleza, obrigado.
Okay.
No question. So could you say something about the primordial black holes? Like, could it be like related with the dark matter or something like that?
Well, the problem is that the most likely primordial black holes that would be formed would be, see, of course, the problem is you need a switching mechanism to average the quantum field. And the switching mechanisms we thought of would be things like phase transitions in the early universe, which occur on a fairly short time scale. And if you have a relatively short time scale, that can lead to large fluctuations. But the mass of the black holes that you're likely to create are such that they probably would have Hawking evaporated by now. So they would no longer be around to form dark matter, but rather that they would have existed for a finite interval and then turned back into photons. But they will still leave an indirect effect, because if you take energy out of the radiation in the very early universe and then you deposit it back into radiation a little later, it can change some of the physical processes that occur. In particular, if you didn't deposit it back until after nucleosynthesis, that could have a fairly big effect on cosmological nucleosynthesis. And there are fairly strict bounds on the masses of very small black holes that would be formed before nucleosynthesis and evaporate after nucleosynthesis. So that's one, looking at indirect effects like that is one way you could look at those black holes. Now, it's true, there is a possibility of creating larger black holes that could still be around today and possibly be dark matter. That's probably a little less likely from this mechanism, unless the quantum stress tensor fluctuations were a trigger for something else, that the large fluctuation triggered the gravitational collapse of something that otherwise was classically unstable. But that's something where more work needs to be done.
Okay, thanks a lot. Let's see. People are too shy today.
I have one question, Carlos.
Yeah, okay. Go ahead.
Yeah, Professor, thank you for your beautiful presentation. And also I would like to ask, what kind of trust can we have when we compare, for instance, this analog of gravitational field in fluids with a real gravitational field? Maybe you talk a little bit about it, but I skipped it while I was doing other things here.
Okay, so the analog here is that the density in a fluid looks a lot like a quantum operator. It looks like phi dot, where phi is a scalar field. So what that means is that then fluctuations of the square density of a fluid are going to satisfy the same probability distribution as a relativistic field theory would. So in this case, this is not so much an analog model for gravity as it is an analog model for relativistic quantum fields, namely where the density of the fluid is behaving like a relativistic quantum field. So phi dot, the time derivative of scalar field, is very much like the electric field. And the fluctuations of phi dot squared are very much like E squared or the energy density squared. So it's modeling the fluctuations in the energy density of the electromagnetic field, for example, which of course can have gravitational effects. Now, it's true that this analog model for a fluid, though, has been used extensively in another context as a model for black hole evaporation. This is first pointed out by Unruh many years ago, that you could create an analog black hole in a fluid, or if you have a fluid flowing in such a way that there's a sonic horizon, it behaves very much like a black hole does. So the Hawking derivation of the Hawking effect predicts that in this analog model, you should create a thermal spectrum of phonons. And there's been a great deal of both theoretical and experimental work looking at this. And there have even been some claims that this has actually been seen in the laboratory and for example, in Bose-Einstein condensates, that there's a group in Israel that did an experiment and seemed to see some thermal spectrum of phonons created in a Bose-Einstein condensate that mimics a black hole. I mean, I don't know how well, except with that experiment has been reproduced by others or not, but at least that's a way of understanding gravitational effects like the Hawking effect through analog fluid models.
Okay, thank you so much for such a detailed explanation. Thank you.
Mm-hmm.
Okay, questions? No. Yeah, I think we don't have questions now. Let's see in YouTube if someone wrote something in the YouTube comments. No. No, I can see no question on YouTube, so. Well, so I think if I have no questions anymore, we should just thanks Professor Ford, thanks a lot to come here to participate from our international symposium. And now John, say something.
Yes, Professor Ford, thank you so much. It was a pleasure to have you here with us. And thank you for accepting our invitation and for this beautiful talk. We are going to be pleased if you could also send us the slides so we can share with people at our website.
Okay, probably the PDF file is best, isn't it?
Yeah, it can be.
Okay, I'll create a PDF file and email that to you.
Thank you, Professor.
Mm-hmm.
Okay. So we still have 3 minutes. So I'm just going to set up here. We have 3 minutes for the next presentation.
Okay, I think if there's nothing else for me, perhaps I'll say goodbye now then.
Okay, Professor. Okay. Thank you. Thank you.
My pleasure speaking to you. So.
Okay, thank you, Professor.
Okay. Okay.
See you.
Okay. Goodbye.
Bye-bye. Okay. Okay, so now we are going to have Professor Dionisio Bazeia from UFPB. Professor, obrigado por ter vindo.
Hi, John. How are you?
I'm fine. Trying to take good care in this pandemic life.
Sure. We should. The virus is around.
Yeah. No, it's more dangerous than ever now. So thank you so much, Professor, for being here with us. I'm just going to stop the recording and I'm going to start it again.
Before we start recording, can I try to share my slides to see
yes.
it?
Yes.
Yeah, sure. You can use this button here.
Yes. Can I do it now?
Yes.
Is it there?
Yes, we are seeing.
Let me see if I do this. Is it okay?
It's okay for me.
Okay.
Perfectly okay.
The sound is okay too?
The sound is also good for me.
It's good. Good for me too.
Okay, I'm ready.
Okay, I'm just going to start the recording then. And then I will ask Carlos to introduce you. Okay, so now we are going to have a lecture from Professor Dionisio Bazeia. So Professor Carlos Bessa, please, you have the word to present our speaker.
Okay, thanks a lot, Professor Bazeia, to come here to join us this symposium. Professor Dionisio Bazeia is professor from Federal University of Paraíba in João Pessoa, northeast of Brazil, and he got his PhD in physics at São Paulo University. And then he had a couple of postdocs at MIT, both at MIT. So thanks a lot, Professor, and have a nice talk. Well, you have about 25 minutes, I think.
Okay. Yeah. Thank you, Carlos Bessa. Thank you, João dos Santos, for inviting me to talk to you. And my talk will be on some recent results we have on magnetic monopoles. This is a collaboration with Gonzalo Omo from Valencia University and Mateus Marques and Roberto Menezes from Paraíba University. And my work is supported by FINEP, FAPESC, PB, and CNPq. I will first talk a little bit about some motivation why we are studying magnetic monopoles. Then I will make a brief introduction to the standard magnetic monopole results that we have. And then I will go to some modified models, 1, 2, and 3 that we have studied recently. As a motivation, I want to remind you of a paper by Witten in the 1985, where he duplicated the symmetry. He considered, cosmic strings, but he duplicated the symmetry. I'm using the letter S here to mark the symmetry. And he duplicated it with S cross S to get new features. And more recently, in 2013, Schiffman did something similar. He used the symmetry and enlarged or enhanced the symmetry, adding more degrees of freedom and making it S cross Z, also to get new features, okay? This is the main goal of something is going wrong. Okay, but the main goal of our modification is to add internal structure to well-known the structure. In particular, we are going to focus on, say, on magnetic monopoles. And the main modification do is to add, say, a new function, a function f of the scalar field, to the, say, Maxwell-like contribution to the gauge field. This will change the electromagnetic properties of the medium, okay? And I remind you that this was done in the, say, in the 1970s by T.D. Lee, when he was interested in studying bag models for quarks, and later in the beginning of the 1920s by Lee and Nunn and myself, studying, say, features of Maxwell and Chern-Simons vortices. And more recently, in 2014, Medford and Horowitz also used this kind of modification to study holographic insulator. So I'd say we are not alone in this. And more motivation appears in 2018, when in 2009, when some people discovered, say, magnetic monopoles in spin ice systems in condensed matter. This opened a new boom for the study of magnetic monopoles. Right? And for those of you interested in magnetic monopole, I reminded of those two papers, review papers on magnetic monopole, one in 2006 and another one this year in artificial spin ice system. Okay. So we are not alone. Okay. The study of magnetic monopole was started with, sorry, I have a problem here. Something is not, okay. Okay, I have a problem. Okay, I got it. Okay, the standard magnetic monopoles, was studied in the 1970s, in the middle of the 1970s by Tufts, Polakov, Prasa and Sommerfeld and Bogomon, some very well known. And the magnetic monopoles appears in 3+1 dimension in SU2 model, but this is somehow complicated. So I will make a warm-up using a very simple model with a single hero scalar field, phi. With this model, now I'm in 1+1 dimension, and then I look for the equation of motion for this model. The equation for motion is this one. I suppose the solution are static solutions, so the equation of motion becomes this one. This is an ordinary differential equation, nonlinear ordinary differential equation. Okay. And then write the energy density of this model, and the energy density gets this part which comes from here. This is the gradient contribution to the energy density plus the potential contribution. Now I suppose that I have a function W of phi, and that I can write the potential in this way, as the square of the derivative of W with respect to the field. If I do this, then I can rewrite the energy density in this form. Okay. As I complete the square, say, the square of the phi dx is this part of the energy density. The square of the second part is this part for V given in this form. And the crossed term here gives you the W d phi dx with the minus sign. So I put this, the W d phi, which is the W d phi dx. So I keep the equality valid in this case. So now I look for the energy density. I look for the energy density, and I see that it has a, say, surface contribution plus a squared of a real contribution. So this is not negative. And then I get this. If I force the field to obey this equation, I get the energy density given by this. So I get, say, minimum energy solution for solutions of the first order differential equation, which solves the equation of motion in a very simple way. Okay? So this is, say, the methodology. This is the procedure you have to work with. We take a model, you look for the equations of motion, we write the energy, and we work out with the energy density to writing this in a form like this one. Then we get first order differential equation that solves the equation of motion for minimum energy solutions. Okay. Now, if I go to the magnetic monopole problem, okay, my model is a little bit more complicated. Say I have a non-abelian SU2 symmetry. So I have a gauge field with little a is 1, 2, 3, okay, for the internal degrees of freedom. Say the covariant derivative is this one. So I have a triple of scalar fields, and I have, say, also a triple of gauge fields. And I do the ansatz here. Say, I write the scalar fields in this form. So I have just one, say, capital H as the only degree of freedom to connect with to the scalar field. And I do a similar thing. I write the gauge field in this form, and now I also have just one degree of freedom, capital K, here, connected with the gauge field. If I do this, the equations of motion that I have for this complicated model are those on. Say one for the gauge fields here, represented by K, capital K, and the other one for the scalar field. Even though I am doing a very important reduction here, my equations of motion are very hard to solve. They are coupled nonlinear differential equation. So we go in the same way I told you right now. We look for the energy density. We work with the energy density, and after some calculations, analytical calculation, we can write the energy density in this way, as the square of something related to the, say, the scalar field, and the other contribution related to the gauge field, plus the potential here, plus a surface contribution, which I'm not going to tell you which is. But if I put the potential to 0, I send the potential to 0, and I also force those two equations to be obeyed, say which they are written here, those two equations. I'm using just the one of the signal here, okay? And I got those two first-order differential equations. Yeah? And I can solve them analytically. This was done by Praça and Sommerfeld and by Bogomolov too, in the middle of the 1970s. But I can write the solution analytically, and the solution are minimum energy solution. So the solution are stable. And here I am just depicting, say, a section, a planar section of the energy density of this solution, of the standard magnetic monopole solution, which is here. Okay. Now I go to the first model we studied in this work here. This what we did. We took this the same model, S2 model, and we added, say, this P of phi here and M of phi. We had to do this to get to the Bogomolov procedure. Okay. We had to add M here, controlling the covariant derivative, and P here, controlling, say, the gauge field kinematics. If I look for a static solution, and if I put it again V to 0, and if I write M as 1 over P, okay, then I get, for P given in this form, I get two first-order differential equations. So we shall minimize the energy of the solutions. And in this case, for P is equal to the phi, is proportional to phi, we could write analytical solution. And the solution is depicted here. It's similar to this one. But you see, we have this, say, the same quantity of black ink that we have here, we also have here. So we call it this solution small monopole. Okay, because the monopole is smaller than this one. Okay, the energy density is more concentrated around its core. Okay, this was the first model, but we studied another model with the same Lagrangian density, but just changing the P, this function P here, this function P here. We put this linear and here inversely proportional to the square of the scalar field. In this case, we found two first-order differential equations. Okay, but now the equations are much harder to solve, and we had to solve them numerically. But we did it. We solved the solution numerically, and we found the solution, this solution, which is depicted here. The solution has the same quantity of black ink here and here and here. Okay? But in this case, there is, say, a hollow part of the solution. The solution becomes a shell, say, with an empty part in its interior. We should call it the hollow magnetic monopole. After doing this, we got another idea to write, say, bimagnetic monopoles. And in this case, we followed Witten ideas, and we took the original S2 symmetry, we doubled it, and to write S2 cross S2. Say, instead of having an F squared contribution, we added two F squared contribution. The new contribution is, I'm using calligraphic letters to represent the new, say, degrees of freedom. And we need, say, to change the gauge field to two other gauge fields, one for F and the other one for calligraphic F. We did this, we did the same for the derivative of the field. Okay. We changed it with two derivatives, one using the A field and the other one using the calligraphic A field. And you had to double the degrees of freedom for the scalar field. And we are using here phi and chi. So, but if you just do this, we have no interactions between the two sectors. So we added the interaction between the two sectors, adding the calligraphic P to the second sector and P to the first sector, but we changed it. Instead of write P of phi of the field phi, we include the P of the field chi. So the interaction between the two SU2 symmetries is given by this P of chi here. So we have SU2 here and SU2 here, which interacts with the other SU2. So those are the two, say, gauge fields which are interacting in this way. When we did this, we wrote now two first-order differential equations for the first sector and two first-order differential equations for the second sector. And then I write them here. Say for the sector with calligraphic and capital letters, okay, is here the two first-order differential equation. And for the first pair of equation for the first SU2 symmetry, we have this part of equation. And you see that the interaction is here. Okay, capital H and capital K sees the calligraphic H, sees the other sector, SU2 sector, in this, from this P here. But the second part of equations, they are independent. Say, this SU2 symmetry acts independently of the first one, but they change the first sector. Okay? So we can write this and solve this, say, with the blue color here that I'm showing, say, for the first equation. This is a, say, a standard monopole, or we can choose P to write a small monopole, or we can choose P, this P here to write, say, hollow monopole, which is changing hollow to shell here. Okay, so the second pair of first-order differential controls, say, the standard monopole, the small monopole, or the hollow monopole. And the other field, we control it by adding this the red part of the solution, which is the bimagnetic solution. There is a magnetic property represented here by the blue color, and the other magnetic property represented here by the red color. Okay, this is all I have to say. So thank you very much. Obrigado.
Okay, thanks a lot, Professor. Now we have time for questions. You can write the question here in the Q&A section, or if you prefer, you can raise your hand, but I can see the raised hand here. My panel, but I think João can. So questions? Oh, I think I have one here. I'll read the question to you, Professor Bazeia. It's Alexis Roa Aguirre. I'll read you what he is saying. I would like to know what happens with the magnetic charge. What happens with the magnetic charge?
Alexis, thank you for the question. I don't remember right now because this was done 2 years ago, but I guess we did not look at this, the magnetic charge of the solution. Say you can see the topological charge of the solution, okay? But since the topological charge of the solution depends on the asymptotical behavior of the fields, I guess they are not modified by the modification we have done. But I'm not sure about that. That's a nice question.
Okay, thanks. Thanks, Professor. Thanks, Alexis. He said thank you to you, Professor Bazeia. Okay. And let's see, more questions. We still have time. Let us check in the YouTube. People can make questions in our YouTube channel. Just Danilo say Grande Dionisio.
Carlos, I have one question.
Okay, go ahead.
Professor, before the question, thank you so much for this beautiful presentation.
Sorry for I was kind of nervous.
No, it's
I'm alone at home here, so
it was really fun. It was really beautiful, and the results and graphics and these physical analyses are also really beautiful. I would like to ask about that graphics that you showed in the end of the presentation. When you have those double, let's say, monopoles. If it's possible to use some of the parameters to that you are putting in the Lagrangian, yes, this one. Yes, if it is possible to use these parameters to, let's say, establish a critical behavior for these kinds of different structures for the monopoles.
Could you repeat it, John? I could not follow quite well your
Yeah, sure.
This is the model. See?
Sure, yes. I'm seeing that you have two scalar fields there.
Yes.
And I mean, I think that this is why you are having this kind of two shells for the monopoles.
The two shells, in fact, comes from the scalar field, but through the P, the function P.
Okay.
It's the mechanism. I will try to explain this. The mechanism is like I can go to the simple case of a single scalar field. For instance, if you put here a function of the field, say of another field, you add another scalar field, and the second field modifies, they say, the kinematics of the first field by a function of f of chi, say. Mm-hmm. Okay? So if this contributes to the energy in this way. See? The energy here. If you put f of chi here, it is going to appear another term here, f of chi here, yes. The energy. If you choose the f of chi properly, you may say send the field the f of chi to infinity. Suppose you find this, say 1 over chi squared. Say when chi is 0, this is infinity. So this is going to make the energy ill-defined. And the only way to make the energy well-defined is to make the derivative of the field goes to 0. See?
Mm-hmm.
This is the mechanism. So to control the energy of the solution, okay, you have to say to make the solution small or to make the solution empty inside. Say you can make the solution with several shells, shell on shell on shell, and etc. The mechanism for doing this is just the function, say, P of phi here.
Mm-hmm. Okay, I see.
I opened everything for you.
Yes, thank you.
It's not particular depending on the which is the scalar field.
Mm-hmm. But how is this function that you put, let's say, to increment the Maxwell law?
For instance, in this case, I put, say, 1 of phi squared.
Mm-hmm.
1 of, say. So when phi is 0, okay, it makes the phi is 0 at 0. Okay? So it makes the empty space here. Okay.
Okay.
This is the way you control, say,
nice.
the form of the solution.
Nice. I guess I realize it now. Okay, thank you so much, Professor, for the detailed explanation. I guess we have time for one more question if someone wants to make one more question. No? Okay, so I would like to thank you again, Professor Dionisio, to be here with us. It's really a pleasure, and feel always welcome in our events. You are a very important part of our history here in UFCG, so thank you so much for everything.
Thank you. Thank you all from UFCG. You know I have a good friend there. Okay, now I'm leaving then. Thank you.
Okay, Professor. Thank you. Well, now let me just recheck here. And yes, now we have a break, 30 minutes break until the next sections. It's going to be the final sections of lectures of this day. So I'm going to stop here the live transmission, but I'm going to leave the room opening, so you can stay at the room as you wish, and then we go back in 30 minutes.